Good morning, good afternoon, good evening. Whenever you are watching this video, let me welcome you all to our channel Future Endeavors. Okay, so in today's class, we are going to discuss about the displacement, or rather we can say displacement versus distance graph. In the previous class, we have discussed about displacement versus time graph. In today's class, we are going to discuss displacement versus distance graph. Okay. So without wasting time, let us quickly move on to the topic. So please take out your pen and copy, and if necessary, please make the required notes. Okay, so make the heading, it's displacement, distance graph, displacement distance graph. Okay, displacement distance graph. Fine. So what is displacement distance graph? So in the previous class we have said that we have give a jerk to a string attached to a certain one end, and due to that jerk a wave has been created in the string or the rope, and we have focused on a particular point on the string or the rope. We are just noting the displacement or the movement of that particular point on that string or rope with respect to time. In today's discussion, we are going to refer, or we are going to discuss about the position of the individual points on the rope or the string at a certain instant of time. So at that particular instant of time, try to understand this, at that particular instant of time, we are just seeing the whole frame together, not a single point. We are not focusing on a single point, rather we are actually observing the displacement or the position of each individual particles on the string or rope at a particular instant of time, and that is how we get a displacement distance graph. Okay, so just consider the fact that there is a rigid support, okay, and the string was initially attached here, okay, at this distance point, and at this free end we give a jerk. So after giving a jerk, just if we capture a particular moment, the string would look like something like this. Okay, something like this. This is the free end, so it will look like something like this. So if we actually plot the position of the individual points on the string or rope with respect to the distance from the point where we are holding, okay, or point where the string has been attached firmly to the support, we get the displacement distance graph. So you will be quite surprised that if we just plot this graph, displacement versus distance, okay, what we actually observe is that the curve is something similar to the previous graph, that is the displacement time graph. Okay, so on this x-axis we are taking distance. What distance? We are taking the distance of the individual points. Okay, individual points from the starting point or the end point, from any point. You can consider this has to be the, if you are considering the free end of the wire, of the ring, of this string or the rope as the origin, then as you move towards the fixed end, the distance from the hand while you are holding it increases, and correspondingly we plot the position of the points on that rope. Okay, so if you consider, say, if I consider the total rope or the total string is of say length 50 cm. Okay, fine. So if I say that we consider a point 3 cm from the point where we are holding it. So suppose this is the point. Okay, 3 cm, from 3 cm on the rope we move and we reach to a point here. We see that the point on the rope, which is at a distance of 3 cm from where we are holding, is actually displaced at a certain height from the mean position. Okay, at a certain height from the mean position, and it is observed that if we just move on, we will be getting something like this, that if we consider this starting point as to the origin, then the particle which is at the origin or at the 0 cm distance is having a zero displacement. So you get something point like this. As we progress with the distance, we see that some particles are displaced from the mean position at a height like this, then some particle are displaced from the mean position at a height like this, and like this it reaches a maximum displacement from the mean position. Then again, if we just move or progress further, we will see that there will be again next particle which will be at a certain displacement from the mean position like this, then certain mean position like this, and then again we will be coming to a point where we will be seeing, see, if we just consider this point, okay, if we consider this point, say this one, now this point is again at a certain distance from the point where we are holding it, and if you see that point on the rope or string, it is again at the mean position. So it actually, what happens, we are plotting the position of the individual points on the rope or string along the distance. Okay, then if we can move further, we will see that there will be a downward trend of displacement like this, downward trend, and then again downward trend, and then to a certain maximum displacement on the negative side of the mean position. And then again, if you plot the next point, it will be somewhat upward like this, somewhat upward like this, and then somewhat again on the mean position. So the graph is actually something like the previous graph we have plotted, when we have plotted the displacement versus time. Okay, we have plotted that displacement of a particular particle with respect to time, and we have obtained something similar graph like this. So this is actually the graph, the shape of the graph is actually somewhat similar, okay, but actually here we are plotting the displacement versus the distance. So on the y-axis we are taking the displacement, and on the x-axis we are taking the distance. Sorry. So basically, it will be observed that the similar kind of graph is obtained. I hope you can understand how we are actually plotting the displacement versus distance time graph. Okay. So if you consider this kind of graph, what is actually this distance showing? Okay, so if I consider the graph a little further and plot it a little more, and so we will be seeing something plot like this, similar plot like this. Okay, if we just extend the graph, just let us extend the graph like this. Okay, then it will be seen that the curve will again move up. Okay, the curve will again move up, go to the maximum position, and then again come down, and then again, okay, like this, something like this will happen. Okay, something like this kind of graph is obtained. Okay, so actually what is happening? So if I consider say 2 points on this graph. Okay, so this is basically displacement. Okay, displacement, sorry, this is the distance. Okay, this is the distance we are plotting on the x-axis. Now if I consider 2 points, point A and point B, okay, point A and point B, what does this distance denote? Actually this distance denotes the wavelength of the wave. Why the wavelength of the wave? Because see, this is, if we consider a longitudinal wave, this is one compression region, this region is showing one compression region, and this region is showing the next successive compression region. So actually the length between two successive compressive region is denoting, okay, the wavelength, isn't it? Similarly, if we consider this downward position for the longitudinal wave, this is the region of rarefaction, and this is also the region of rarefaction. And if you consider this distance, this is also the distance of one wavelength, isn't it? For transverse wave, will be considered, the position A can be considered to be as the position of crest, and position B also be position of crest, whereas C and D, if you consider C and D position for a transverse wave, these are the positions of the trough. So in this way, we can actually get the wavelength of the wave using the displacement distance graph. Something similar we have also find out that in case of a displacement time graph, the length between the two successive compressions or two successive rarefactions was indicating the time period of the wave, isn't it? Time period of the wave, because in that case, in x-axis we are taking the time. So in this way we can actually analyze the graph or analyze the wave that is moving forward, whether it is what kind of wave it is being generated. Generally the sound waves that we hear are of this nature, and this kind of graph is, as we know, is called sinusoidal graph. Okay, this kind of graph, the shape of this graph, okay, the shape of this graph is referred to as sinusoidal graph. Okay, sinusoidal graph. Why it is referred to as sinusoidal graph? Because so some of you may have learned trigonometry by now. So In trigonometry you have seen the sine function, cos function, tan function. Okay, if I consider the sine function actually and plot the sine function on a graph, we will get something shaped like this, curve like this. Okay, so this curve, this kind of shape denotes the sinusoidal graph. Okay, so this is sinusoidal graph. So both displacement time graph as well as the displacement distance graph are actually having the same nature, but they are carrying different meanings. They are carrying different. If we analyze them, we will be getting different informations from these two graphs. For this, from the displacement distance graph, what we are getting the wavelength. Okay, and from the displacement time graph that I discussed in the previous class, from that we get the information about the time period. Okay, so from two separate graphs we can actually find out or analyze the time period and the wavelength of the wave that is being traveling. Okay, or that we are analyzing. So this is the displacement distance graph. So I think the concept by now is clear to all of you. The remaining portion of the sound chapter will be covered in the next video, and I hopefully consider that in the next video we will be finishing the sound chapter sound, and we will be doing some of the numericals that are present in this chapter, okay, or related to this chapter. Okay, so till then, if you have any query, please do mention it in the comment box. We will be happy to solve your problem. Okay, till the next video, goodbye, tata, thank you.